Hello, we are going to be talking about improper integrals, chapter 8, section 8. I want you to look at these two regions. These two regions, do you see that they are infinite regions? They start at 1, they are going to go until infinity. Look, there's no end to it. So this is an infinite region, kind of, right? It looks like an infinite region, but we don't know whether the area underneath this curve is infinite or not. Even if it looks like it's infinite, we don't know unless we compute. Okay, and here let's look at the second picture as well. This is the graph is y is equal to 1 over square root of x, and I want you to look at this region here. Do you see that there's an infinite part going up here? So we are interested in, can we find the area of this infinite piece? And is the area finite or is it infinite? So these are the questions that we want to answer. So how does it happen? Is, look, here here the x goes to infinity here, okay? So when we want to integrate this, when we want to write the integral of this, we should write 1 to infinity of this function dx, okay? 1 to infinity. And in order to write this, we have to write 0 to 1 of this function. Okay, so you see that this is an infinite region, and we are going to write the area 0 to 1, this function, and we don't know whether this the value of this area is finite or not. And we'll see how to do those things. And I want to get your attention, one more thing, that look, at 0, this function becomes undefined, 1 over 0, right? This will be important in our discussion. For example, look at this region. This region is looking like infinite. It goes to infinity, like 0 to infinite of this function. But even if it looks like an infinite area, the value is 2, because the function is getting 0 very quickly. So this is like a finite triangle. Let's look at this area. This area is finite, so no problem with that. But in order to get this area, what we do is we are going to just fix a point B and calculate this region, and we let B go to infinity and take the limit of that expression, and we get the area like that. These type of integrals are called improper integrals. There are two types. The first type is as follows. In the first type, you're gonna see the limits. One of the limits or both of the limits are infinite. Look, here one of the limits is infinite, here negative infinity, here both of the limits are infinite. If you see infinity in as one of the or both of the limits, then you can call them improper integrals first of all, because you are integrating over an infinite interval, and you're not sure whether the area you get is infinite or not. So therefore it's called improper integral of type 1. So if it continues from a to infinity, then how do we integrate is as follows: a to infinity f of x dx. For the infinite part, we give it a name b. We partially calculate this integral, and then we let b goes to infinity, like in here. Like, instead of calculating this directly, we just fix a b, we calculate this part and find the value. The value is looking like that, and then we let b goes to infinity. E to the negative infinity, this is going to go to 0, so the value is 2. Okay, so similarly, we may have negative infinity as well. So we are going to treat it similarly. So we are going to just say, instead of negative infinity, we are going to consider a. Okay, a negative infinity to b. You take the limit as a goes to negative infinity. Okay. We find it. If you have infinities on both sides, then you have to separate it into 2, because it's easier if you do that. Then in each one, you just look at 1 and 2 here and solve them accordingly. Okay. At the end, the integral could be divergent or convergent, we don't know. However, if you look at the third one, if this is divergent, if this is convergent, then the whole integral is divergent. If both of them are convergent, then this is convergent. If both of them are divergent, then this is divergent, okay? So let's look at this first example. As you will see, we would integrate from 1 to infinity, but we stop, we fix a point B, and we just want to calculate this first and find the value in terms of B, and then we take the limit as B goes to infinity, because B goes to infinity here. Do you see that? And here, look at that, we have infinite x values here, right? And it looks like an infinite area, but it is not. Look, the area becomes pi. So this integral can be written negative infinity to positive infinity, 1 over 1 plus x squared dx. But we apply the definition, and we are going to see it's pi. It's not an infinite integral. Let's look at this. This is the second example we saw today. 1 over square root of x. So we just fix a here. A here as a goes to infinity. We just calculate this area, and then we let a go to 0. No, not infinity. A is getting closer to 0. Okay? This piece actually has an area 2 minus 2 square root of a. When we let a goes to 0, then we got 2 as the area. We have the second type, which is improper integrals of type 2. If it's a continuous function on the interval, half open interval, but it's going to continue at the point A, okay, like this one. So this is not continuous at 0, okay? So this is actually this one is of improper integrals of type 2. Then in this case, we are going to use limit again. For this problematic point, we are going to call it C. We are going to just calculate the integral for a piece, and we let C goes to A plus, because we have the discontinuity on the left. If the discontinuity on the right, then we are going to again let C, but C is going to approach to B from the left. And we may have discontinuities on both ends, or in between, I'm sorry. Somewhere in between, C is a point in between, and if it's discontinuous at C, then we are going to separate this integral into two pieces, A to C and C to B, and we treat this separately like in 1 and 2. Okay? If these integrals have finite value, we call them convergent. If they don't have finite value, we call them divergent. Let's look at this example. This function actually, as x approaches to 1 from the left, this function is going to go to infinity. Look. So we have like an infinite region in here. Okay? So we fix a point B that's close to B, and we calculate this integral, and then we let limit B goes to 1 from the left. Okay? And let's look at this. We have this 0 to 3, this function, but at this point 1, there's a problem. At 1, there's discontinuity. So we are going to separate this integral into two, 0 to 1, 1 to C. And then at 1, there's a problem, so we are going to take a point before 1, and call it B. And we just calculate this region and let B approaches to 1 from the left. And also here we are going to just write an integral from C to 3, and C is going to, and we are going to take the limit as C approaches to 1 from the right. Okay? And then the answers are going to be, are going to follow. If both of them are finite, we are going to add them up. If one of them is not finite, then the answer is divergent. What is this? Okay, we want to talk about the direct comparison test. let's say two functions are ordered like that. They are positive functions and they are continuous from a to infinity, and g is bigger than f. If since g is bigger than f, if the integral underneath, if the area underneath the curve is finite, then the area underneath the curve f is going to be finite too. In other words, the integral a to infinity g is finite implies a to infinity f of x dx is finite. Finiteness means convergent. On the other hand, if we know that if the area underneath the curve f is big, very big, which means the integral is divergent, then, and since g is bigger, then the area underneath the curve g is going to be very big too, so it's going to be divergent. So this direct comparison test. So there is one example here. For example, you look at the e to the negative x squared. Look, it becomes below the function e to the negative x as x goes to infinity. So after 1, e to the negative x is bigger than e to the negative x squared. And let's check whether e to the negative x squared is convergent from 1 to infinity. Let's calculate that. Negative e to the negative x, if you look at the antiderivative, 1 to infinity, and it's finite. So since e to the negative x is bigger than e to the negative x squared after 1, this would mean, and before 1 these are finite already, you don't have to worry, but the problem is after 1, because as x approaches to infinity, we have an infinite region here, and we don't know whether it's a finite value or not. But e to the negative x is bigger than the function e to the negative x squared. By the direct comparison theorem, actually, since this is a convergent, 1 to infinity e to the negative x is convergent, and 1 to infinity e to the negative x squared is also convergent. So that's going to tell us that the area underneath the curve for a blue function e to the negative x squared is finite. So we did this by looking at the direct comparison test. Okay, this test. Alright, and there's another test to compare the integrals. Let's say we have two functions, they are positive functions, they are continuous on the interval a to infinity, and we look at the limit of the ratios as x approaches to infinity. Okay, we want to know how fast they go in compared to each other. Okay, how fast they get enlarged. Okay, and if the ratio is L is a finite number, then they behave the same, because they differ only by a constant you can consider in the infinity. So their integrals are going to be acting similarly. If one converges, the other converges. If one diverges, the other diverges. So let's see whether we can find an example. Let's look at the ratio of the two. The ratio of the two functions is 1. So we can easily calculate the integral from 1 to infinity of this negative 1 over x. 1 to infinity, so this is a finite integral, so this is going to tell us that 1 over 1 plus x squared, the integral of that is also convergent, since the integral of this is convergent by limit comparison test. Yeah.